So Sarah wanted me to record a quick little video explaining this joke here, even though sometimes explaining the joke is a little bit more painful than getting the joke. But what we have here is a digital logic circuit, and in digital theory, we perform logic functions in a binary fashion. Computers, run on their little ones and zeros. So everything has to be either true or false. And we can make a combination of true or false statements to get to the answer that we want to get to logically. We do that with logic gates in digital theory. And each one of these symbols on here is a different kind of logic gate. So to start with, I thought I'd show you some of the other logic gates that we have access to perform our logic functions. And you can see the symbols for them here. The first one we have here is a NOT gate. A NOT gate's job is to take a given input and invert it to its opposite state. So if we had a true statement over here, the logic gate would convert it into a false statement. This side would be the input side of the logic gate, and this side is the output side of the logic gate. The next one in the line is an AND gate. What this does is it compares the two inputs, A and B, to determine some sort of logical function. And says that this has to be true and this has to be true in order for this to be true. And you can see down from the truth table that if A is false and B is false, then X is false. If B is false and A is true, X is still false. The only state where X is true is when A and B are both true. And down the line, we have a bunch of different other gates that we can use in our logic string, our combination of logic, to get to a desired result. Right here is an OR gate. It looks kind of like the Star Trek badge. And its job is to compare these two and determine whether one is on, the other is on, or both are on. Then this one will be true. And you can see it differs from the AND gate a little bit in that all three of these states are true because A could be true, B could be true, or they both could be true in order for this to be true. Let's go back to our little diagram here, and we can see we have an OR gate and we have a NOT gate, and we have our two statements. But our two statements are actually tied together. So the input coming into this leg of our diagram and this leg are both the same statement, but it's been inverted, coming into an OR gate, which will determine if this one is on or this one is on, then this one will be on to answer our question. So what this is saying is to be or not to be is our question. And there's the joke. I know, I told you it'd be painful.